So in that last video, we evaluated the derivative at a point on a function. So we had a value for x to plug in. What we're going to do here is evaluate the derivative as just a function. So we're not going to be looking at a certain point. It's basically creating this whole derivative function that we can work with. And then I'll show you how that can be helpful when we're trying to find the derivative at certain points. So the idea is that when we apply this, before we were plugging in values for x, and in this part we'll be leaving x in. So what we're going to get is this f prime of x function that's going to describe the derivative for all x values of that function. Okay, so again, we're going to use the difference quotient here for calculating it. Next week, we'll probably come back to this example and apply our little shortcuts that we learned then, but we need to be able to do this with the difference quotient. So we have our function x squared minus 2x, and we want to find f prime of x. So to do that, we're going to take our limit as h approaches 0 of f of x plus h minus f of x all over h. So plugging into f of x in that numerator, we're just copying our function down. What can be helpful is maybe we'll do some side work over here of what f of x plus h is simplified instead of doing it within the fraction. So f of x plus h, so our function tells us to take our input squared minus 2 times the input, and for us the input is x plus h and x plus h. So for this x plus h quantity squared, we're going to need to FOIL that out, and we should be getting an x squared plus 2xh plus h squared. And that's coming from evaluating the multiplication of x plus h times x plus h, and then FOILing. So those first values give us the x squared. Outer is x times h, and inner is x times h, so those add up like terms to 2xh, and then multiplying last gives us that h squared. All right, then over here we want to distribute that -2 in, so we're going to have -2 times x and -2 times h. Then we just want to see if we have any like terms here, but we don't have anything. There aren't any terms here where the variables and exponents match up. So this is just going to stay this big expression, x squared plus 2xh plus h squared minus 2x minus 2h. So we're going to take all of that and plug it in for f of x plus h here. So let's go ahead and keep evaluating our limit. So the limit as h approaches 0, because we're still evaluating this limit since we can't plug in 0 yet, where I have f of x plus h, I'm replacing that with that x squared plus 2xh plus h squared minus 2x minus 2h. All right, all of that was our f of x plus h. Then I'm going to go minus, and then our function, and I need to use parentheses here to make sure that that negative distributes with our function x squared minus 2x all over h. All right, let's go ahead and distribute that negative in. So with that, we're going to be getting this limit as h approaches 0 of all of this x squared plus 2xh plus h squared minus 2x minus 2h, and then we'll have a negative x squared and a positive 2x all over h. Now combining like terms, we have x squared minus x squared, so it's just turned to a 0. We have, sorry, I miswrote one of those, which would be a minus 2x minus 2h, And then we have a positive 2x, so that negative 2x and positive 2x cancel out with each other. So we're going to have this limit as h approaches 0. And in that numerator, so what I have left over is this 2xh, h squared, and a negative 2h. We can factor out an h from that. So I'm going to factor out h, which would leave us with 2x plus 1h, and then minus 2, all over h, which means those h's are going to cancel out with each other. So now we just have the limit as h approaches 0 of 2x plus h minus 2. And to finish this off, we're going to evaluate our limit by plugging in 0, which is 2x. Plug in h equals 0 is just 0, and then minus 2. So we get a derivative function of 2x, f prime of x is equal to 2x minus 2, where our original function is equal to x squared minus 2x. So now what we can do is, if I have my original function x squared minus 2x, and I'm interested in calculating the derivative at a bunch of different points, so let's say I wanted to find like f prime of 1 and f prime of 5 and f prime of 6. So like in that last video, that's what we were calculating by plugging in that value for x. But as you can imagine, to go through 3 different difference quotients and do all the work that we did in that last video 3 different times, it's a lot of work. But here we could just use the difference quotient once and end up with this function to describe all derivatives. So then what we can do is use this function 2x minus 2 to evaluate. So if we wanted f prime of 1, that would be 2 times 1 minus 2, which is 0. And if we wanted f prime of 5, 2 times 5 minus 2, which is 8. And 2 times 6 minus 2, which is 10. So we can start calculating all of these slopes of the different tangent lines at different points just by having this derivative function right here. Let's also take a look at the graph real quick. So if we have our original function, x squared minus 2x, and then I graph the function 2x minus 2, what we can do is, okay, here's our parabola. We're going to talk more about graphs in another video and even more in later lectures, but the red parabola, so that's our original function, x squared minus 2. So let's look at that. Actually, I had even plugged it in. So at x equals 1, on the parabola, that's our minimum value, that's our vertex. So if we think about the tangent line there, we'd actually have a tangent line with a slope of 0. So if you look at this blue line that's mapping 2x minus 2, what you can see is that when x equals 0, when x equals 1, y is 0. So how this is relating, the y coordinate from that blue line is matching the slope of the tangent line from that coordinate on the red function. So another spot, the other values I chose were kind of tricky, but like here at 2, 0, we have this kind of nice positive slope coming through here. And if we wanted to know what that actual slope is, we go to this blue line where we have the coordinate 2, 2. So what that tells me is that when x equals 2, the slope of the tangent line is also 2. And then we could just do this for any coordinates. When we're at x equals 0 on our function, we can see there's kind of a negative slope. And in fact, we can see when x equals 0, the slope is a negative 2. So the outputs from the blue line are the slope of the tangent. So that's where we ended up with a function that's mapping all of those slopes. All right. So same process as we did in the previous video, it's just that we have kind of 2 variables in there because we're leaving x in. All right, let's go through another example, and this one's going to require a little dealing with radicals to help us simplify. So Our function is just the square root of x, and we want to find the derivative function. So we want to find f prime of x. So we're going to take the limit as h approaches 0 of f of x plus h minus f of x all over h. This is going to be the same as the limit as h approaches 0, so f of x plus h is just the square root of x plus h, and then minus f of x, which is just the square root of x, all over h. Now, we get stuck here because we can't factor out an h. I still don't want to plug in 0 because my denominator will be equal to 0 and it's undefined and nothing good comes from that. So what we need to use here is a trick that we do with radicals, and specifically cases where we're adding and subtracting separate radicals. The trick, or rather the mathematical term, is multiply by the conjugate. What this uses is the idea of a difference of squares. So let's talk about what a conjugate is. So let's say I had an expression 1 plus root 2. The conjugate of that expression would be 1 minus root 2. So the terms stay the same, but if you have addition, this is using subtraction. If we had started, let's say this was root 3 minus root 4, the conjugate would be root 3 plus root 4. So it's a fancy word for saying if you have addition, change it to subtraction. If you have subtraction, change it to addition. And that's where we're getting this difference of squares. So when we FOIL this, we end up, sorry, it's hard to say this without using the definition of the word itself, but when we multiply them using FOILing, we get a difference of squares. So let's do that with this root 3 minus root 4. So FOILing, our first terms is a root 3 times root 3, so that ends up being just a root 3 squared. And then outer is going to be a root 3 times root 4, and that's going to be positive. But then notice what happens with the inner. We have root 3 times root 4, but it's negative. So those end up canceling each other out because we have like positive root 12 minus root 12 is just 0. So outer and inner ends up canceling each other out, and that's because we have this relationship of same terms, but conjugates, one's addition, one's subtraction. So then our last piece is multiplying the last terms. So I'm going to go minus, so we have a negative root 4 times positive root 4, so that's going to be a negative value, and a root 4 times root 4, so a root 4 squared. When you have a square root squared, it's like the square root of 3 squared is just 3. It's like there's a cancellation of those two symbols. And then minus and root 4 squared. So again, the square root and the square kind of cancel out with each other. So then we're just left with what's underneath the radical, so 4. Anyway, we want to use this property because look at how nicely that we started with something complicated with this multiplication of conjugates, and we end up with something that doesn't have any radicals involved. All right, so let's bring that here. I have my numerator, which is the square root of x plus h minus the square root of x. I want to multiply by the conjugate. So I basically want to keep the square root of x plus h. I want to keep the square root of x for the second term. And we had subtraction in there, so my conjugate should have addition. Whatever we do to the numerator, we have to do to the denominator too, to keep balance. It's like I want to be multiplying by a version of 1. So as long as I have a multiplication of the square root of x plus h plus the square root of x in the denominator, we're still following all the rules because this is really just multiplying by 1. It's just a very complicated version of 1. All right, here we go. So now we have our limit as h approaches 0. Multiplying by the conjugate is going to lead to that difference of squares. So we're going to have this square root of x plus h squared minus square root of x squared. All over, and I'm going to leave these separated, mostly because we eventually want to cancel out that h. So I'm going to leave that factored out, h times the square root of x plus h plus square root of x. Okay, and limit as h approaches 0. Square root of x plus h squared is just x plus h, minus square root of x squared is just x, over h times that square root of x plus h plus square root of x. In the numerator, x minus x is just 0, so those cancel each other out. And then we just have h, and then we have our common factor of h, so those will cancel, leaving us with a big 1 in the numerator. So, limit as h approaches 0, 1 over square root of x plus h plus square root of x. Now we can plug in h equals 0. So now we can evaluate our limit going 1 over square root of x plus h, which is really x plus 0, so square root of x plus square root of x, which is equal to 1 over 2 root x. And we did it! Oh, if you stuck with it, you're gonna be either very relieved or very mad next week when we find basically a step that'll let us do that in about 30 seconds. But this is where it comes from. This is where it's derived from. This is how we can use the rule we eventually get for this, so we can come back and look at these woefully next week. But for now, we gotta do it. So this is a pretty complicated example. This was our first one that wasn't a polynomial too. Like all of our functions so far were even, I think they were all quadratic in some form. So it does get trickier when you leave polynomials, but we'll mostly be looking at these polynomials here, but wanted to make sure we covered this multiplication by a conjugate as a nice little review of those for how to simplify these complicated functions.